Hey everyone, imagine a conveyor belt, but instead of touching the things you want to move, it uses air. That's what this slide is about. It's called a contactless air conveyor, and it's like magic. It can move stuff super fast without even touching it. Think about how this could help factories or warehouses. They could move boxes, parts, or even food without worrying about damaging anything. It would be way faster and more convenient than using regular conveyor belts. So, this contactless air conveyor is a pretty cool invention that could change how we move things around. It's all about using air power to make things happen. As the definition states, air conveyors leverage air pressure or vacuum to transport materials without physical contact. This ensures a fast, safe, and efficient mode of transportation. Now, let's explore some key applications of air conveyors. They are particularly well suited for handling lightweight goods such as containers, boxes, and trays. Furthermore, air conveyors excel in handling sharp or abrasive materials while effectively preventing clogging, a common issue with traditional conveyor system. Finally, let's look at industries that heavily utilize air conveyors. These include manufacturing, recycling, food processing, and packaging, among others. In summary, air conveyors represent a cutting edge solution for material handling, offering numerous advantages in terms of speed, safety, and efficiency. Let's now discuss the advantages of utilizing air conveyors. Firstly, air conveyors require minimal maintenance, exhibit reduced wear and tear. This translates to lower operational cost and increased system longevity. Secondly, air conveyors are ideally suited for high-speed operations capable of exceeding 1,000 speeds per minute. This makes them valuable assets for industries that demand rapid material movement. In summary, air conveyors offer significant advantages in terms of both operational efficiency and cost effectiveness. Let's now dwell into different types and features of air conveyors. First, we have the ring vac system. This type of air conveyor is designed to move solids over long distance with high energy frequency. A notable feature of ring vac is the absence of any moving parts, reducing maintenance requirements. Next, we have the XSPC conveyors. These are particularly well suited for applications involving intimate using and handling of textile materials. XSPC conveyors are known for their reliability and adaptability to various material types. In summary, selecting the appropriate type of air conveyor depends on the specific application requirement, including material type, distance to be covered, and desired throughout. Let's now explore the unique features that set air conveyors apart. Firstly, air conveyors operate contactlessly, ensuring product safety. This is particularly important when dealing with delicate or easily damaged materials. Secondly, reduced maintenance is a key advantage. The absence of moving parts near the material minimizes wear and tear, leading to lower operating costs and increased system reliability. Finally, air conveyors demonstrate remarkable versatility. They can handle a wide range of materials, including corrosive gases, lightweight objects, and even sharp scrap, making them adaptable to various industrial appliances. In summary, the unique features of air conveyors highlight their efficiency, safety, and adaptability, making them a valuable asset across diverse industries. Let's now delve into the various types of conveyors commonly used in material handling. First, we have bulk conveyors. These are designed to transport large quantities of loose materials like sand, gravel, or grains over long distance. Next, we have deck conveyors. These are typically used for moving smaller package items along a flat surface, often within a warehouse or a production line. Moving on, we have neck ring conveyors. These are specifically designed for handling delicate items like food or pharmaceuticals, ensuring gentle and controlled movement. Then we have apron conveyors. These are robust systems used for heavy duty applications capable of transporting large and bulky materials over inclined surfaces. Finally, we have airwayers. These utilize air pressure to move materials contactlessly, making them suitable for handling fragile or easily damaged items. In summary, the choice of conveyor type depends on the specific application requirements, including the type of materials, the distance to be covered, and the desired throughout. First, we have screw conveyors. These are rotatory devices that use a helical screw blade to transport bulk materials like powders, granules, and small pieces. Next, we have belt conveyors. These are widely used and consist of continuous belt moving on rollers to transport materials horizontally or at an incline. Moving on, we have a salt back belt conveyor. These utilize a series of connected cells attached to a moving belt for transporting items that need to be spaced or cooled during transit. Then we have chain conveyors. These use a series of interconnected chains to move objects or material along the defined path, often used for transporting heavy or bulky items. Finally, we have bucket elevators. These are vertical conveyors that use bucket to attach to a belt or chain to lift materials to higher levels. In summary, the choice of conveyor type depends on the specific application requirement, including the type of material, the distance to be covered, and the desired throughout. Let's now discuss the key consideration when selecting the right conveyor system for your specific application. First, we need to carefully evaluate the characteristics of material being handled. Factors like size, flowability, abrasiveness, corrosiveness, moisture content, and temperature all play a crucial role in determining the suitable conveyor type. Additionally, the material's composition, whether it's powders, granules, fibers, or a combination, as well as the particle size, weight, and density, will significantly influence the conveyor selection process. Next, we need to define the primary functions of the conveyor. Is it primarily for conveying, meaning moving materials from multiple pickup points to drop points, or is it focused on feeding, which involves time sensitive and precise material movement, often in batches or at continuous rates? By carefully considering these factors, we can ensure the selection of a conveyor system that is not only efficient but also safe, reliable, and cost effective for your specific application. Let's now discuss the critical factors to consider when designing and implementing a conveyor system. Firstly, a thorough environmental assessment is crucial. This involves assessing factors such as humidity, temperature, vibration, pressure, and potential material hazards. The chosen conveyor system must be able to withstand these environmental conditions and ensure safe operations. Furthermore, the conveyor system must seamlessly integrate into the existing workplace and equipment. Carefully planning is required to ensure proper fit and efficient material flow within the overall production or logistic process. Next, let's consider system design. Modular designs are highly advantageous as they simplify complexity and facilitate easier integration with existing equipment. Additionally, seeking tailored solutions from experienced manufacturers can ensure a system optimized for your specific needs and operational requirements. By carefully considering these factors during the design and implementation phase, you can ensure that your conveyor system delivers an optimal performance, reliability, and longevity. Let's now discuss important considerations for ensuring safe and efficient conveyor system operation. First, let's address product slip prevention. This is crucial to maintain smooth and reliable material flow. Utilizing high friction belts, cleats, or backstopping brakes can effectively minimize the risk of product slippage. Next, we need to consider static electricity, particularly when handling sensitive electronics. The buildup of static charge and can damage delicate components. Employing the anti-static belts or brushes can effectively neutralize static electricity and prevent potential damage. Finally, safety must be paramount. Incorporating features like pop-out rollers, crossovers, and safety mechanisms at points of personal interaction is essential to minimize the risk of accidents and injuries. By implementing these measures, we can ensure that our conveyor system operates safely, efficiently, and reliably, while safeguarding both products and personnel. Let's now discuss vacuum conveyors. As stated here, vacuum conveyors operate by utilizing negative air pressure to transport materials through closed pipelines. This makes them particularly suitable for handling powders and granules, as it minimizes dust accumulation and material loss. In terms of design and operation, the negative pressure within the system helps to minimize leak and contamination. Additionally, vacuum conveyors are known for their compact size, energy efficiency, and self-cleaning capabilities. Furthermore, vacuum conveyors offer several advantages, including minimal wear and tear due to the absence of moving part in contact with the material. This translates to low maintenance requirements and reduced downtime. In summary, vacuum conveyors provide a clean, efficient, and reliable solution for transporting powders and granules, particularly in applications where dust control and material contaminant are critical. This slide shows the diagram of the air conveyor. Photograph of the air conveyor. This shows a top-down view of the entire air conveyor system. We can see a grid-like arrangement of what appear to be individual cells or modules. The object to be conveyed is placed on the surface. A representative unit. This section provides a detailed view of a single unit or a cell within a conveyor system. We can see the dimension of the cell, including the width, depth, and the distance between the cells. Cutaway view. This section shows cross-sectional view of the conveyor, illustrating how the airflow works. We can see the inlet and outlet ports of air and how the pressure is used to lift and move objects along the conveyor. Working principle. Based on the image, it seems that the air conveyor operates on the principle of creating a cushion of air beneath the object to be conveyed. This is likely achieved by pressurizing the cell, lifting the object, moving the object, and releasing the object. The advantages of the design. Contactless transportation, versatility, flexibility, potential applications of the air conveyor system. Manufacturing. Conveying delicate components in assembly lines. Logistics. Moving products in warehouses or distribution centers. Food processing. Handling food items without contaminations. Further considerations. Air pressure control. Precise control of air pressure is crucial for optimal performance and to prevent damage to the object. Energy efficiency. The efficiency of the air compression and distribution system would need to be optimized to minimize energy consumption. Noise level. The operation of the air conveyor might generate noise, which would need to be considered in the design and illustration. Let's now dwell into a theoretical model for futuristic contactless conveyors. The core concept is to utilize air pressure to move objects without any physical contact. Imagine a glossy surface layer with precisely drilled holes. Compressed air is released through these holes, creating a cushion of air that levitates and propels the object forward. To ensure optimal performance, the design features several key elements. Firstly, the size and spacing of the drilled holes can be adjusted based on the weight and size of the object being conveyed, allowing for customization and adaptability. Secondly, for enhanced stability, the system incorporates sides, rail, and inclined frames to prevent the object from deviating from its intended path. Finally, for added control, optimal pneumatic pistons can be integrated to provide additional propulsion or steer to object movement. The innovative approach offers several potential advantages by eliminating direct contact. We can minimize wear and tear on both the objects and conveyor surface. This contactless operation can also be highly beneficial in industries where hygiene is paramount, such as food processing and pharmaceutical manufacturing. However, it is important to acknowledge these challenges. Implementing such a system would require precise engineering and control of air pressure and flow. Energy consumption and the initial investment cost might be higher compared to the traditional conveyor system. Moving forward, research and development efforts should focus on building and testing prototypes to validate the theoretical model and address any practical challenges. Optimizing air pressure levels, flow patterns, and energy efficiency are also critical areas for further investigation. Let's now discuss the components and benefits of this innovative contactless conveyor system. As outlined here, the system comprises several key components. These include air pumps to generate necessary air pressure, hold sheets that form the levitating surface, support frames to provide structural stability, pipes for air distribution, and various fasteners like nuts and bolts for assembly. Moving on to the benefits, this contactless approach offers several distinct advantages. Firstly, it enables high-speed, frictionless transport of object, minimizing wear and tear on both sides of the object themselves and the conveyor system. Secondly, the reduced friction and minimal contact points translate to lower maintenance requirements and enhanced durability, leading to significant cost savings and increased operational efficiency. In summary, the combination of carefully selected components and the inherent advantages of contactless operation make this system a promising solution for various material handling applications. Let's now delve into air flotation system for optical glass inspection. As outlined here, the mechanism involves both utilizing positive and negative air pressure to maintain a stable airflow, enabling non-contact movement of the glass. However, one of the key challenges associated with this technology is the potential for pressure variation to cause material deformation in the delicate optical glass. To address this, researchers are focusing on optimizing nozzle spacing. The strategic placement of air nozzles aim to create a more uniform and stable air cushion, minimizing the risk of deformation. Current research efforts are centered around understanding and predicting pressure distribution across the glass surface and ensuring optimal material stability. These findings are crucial for precision tasks such as defect detection, where even minor deformation can significantly impact the accuracy of the inspection process. In summary, air flotation systems offer a promising approach to handling and inspecting delicate optical glass. Continued research and development in this area will be instrumental in refining this technology and enabling more precise and efficient manufacturing process. This slide shows the image of the optical glass conveyor. Let's now delve into mathematical model aspect of innovating contactless conveyor system. As depicted in the diagrams, the mathematical model provides a crucial framework for understanding and optimizing the system's performance. Figure A and B illustrates the geometric parameters of the individual cells or models within the conveyor. These parameters such as pocket depth, sidewall, thickness, and dam height play a significant role in determining the airflow dynamics and the levitation force generated. Figure C presents a cross-sectional view highlighting the key components and airflow pathways within a single cell. The mathematical model would involve equations governing the flow of air through the inlet, its interaction within the object, and its subsequent exit through the outlet. By incorporating factors like air pressure, flow velocity, object weight, and geometric dimensions, the mathematical model can predict the levitation force, stability, and overall performance of the conveyor system. This model can be used to optimize the design by adjusting parameters to achieve desired performance characteristics such as maximizing levitation force, minimizing energy consumption, and ensuring stable object movement. In summary, the mathematical model serves as a valuable tool for understanding, predicting, and optimizing the performance of this innovative contactless conveyor system. Let's delve into the critical aspect of pressure distribution within air conveyor system. As illustrated here, the experimental apparatus including a measuring table with a sliding bar for precise pressure readings. This setup secured using an elevating table and pin clamps for stability allows for accurate measurements of pressure and characteristics. Analyzing the pressure distribution reveals some key characteristics. Firstly, we observe a symmetrical pressure distribution along the width of the conveyor system, while the distribution along the length is often non-symmetrical. Secondly, the gap thickness between the objects and levitating surface has a significant impact on pressure amplitude. A narrower gap leads to high viscous impedance, resulting in increased pressure within the system. Finally, the effect of suction flow rate Q2 on pressure distributions are noteworthy. An increase in Q2 reduces the air escape to the dam area, consequently lowering the overall pressure within the system. Understanding the pressures characteristics is crucial for optimizing the design and operation for air conveyor system. By carefully controlling parameters such as gap thickness and suction flow rate, we can achieve optimal levitation forces and ensure efficient and reliable material transport. This slide shows a schematic of the apparatus for pressure distribution measurement. The other slide shows the schematic of the apparatus for the viscous force measurement. Let's now explore the diverse application and key advantage for air conveying systems. As outlined here, air conveying systems find extensive use in various industries. These applications include venting gas, hopper loading, and trim removal. They are also widely used for handling a broad range of materials including food ingredients, coal, grains, and abrasives. Moreover, air conveying systems are particularly valuable in material transfer within industries, especially if challenging environments such as those involving chemicals and corrosives. Now let's discuss the significance of these systems. Firstly, air conveying offers dust-free and gentle material handling, minimizing product damage and contaminations. Secondly, these systems are designed for reliability, hygiene, and low maintenance, resulting in reduced operational costs and increased efficiency. Thirdly, air conveying systems are compact and flexible, capable of handling a wide variety of materials from powders to tablets and capsules. Finally, they offer cost-effective illustrations and operations compared to traditional material handling methods. In summary, air conveying systems provide a versatile and effective solution for various material handling challenges across diverse industries. This slide shows a centrifugal pump working principle with a diagram. Let's now discuss the key factors to consider when selecting the most suitable air conveying system for a specific application. First, we need to carefully evaluate the material characteristics. Factors such as particle size, density, moisture content, and explosivity will significantly influence the design and performance of the system. Next, we need to consider operational factors. This includes the conveying distance, but both horizontally and vertically, the required air pressure and velocity, and the desired transfer rate and capacity. These factors will dictate the system's size, power and requirements, and overall efficiency. Finally, environmental and economic considerations are crucial. We must access space constraints, energy consumption, and long-term costs associated with operation and maintenance. Moreover, ensuring health and safety measures such as fire and explosion prevention is paramount. By carefully considering these factors, we can select an air conveying system that is not only effective and efficient, but also safe, reliable, and cost-effective for the specific application. This shows the 3D model. In conclusion, a contactless air conveyor system has been successfully developed for transportation and position of planar objects. The study has correlated the viscous force generated within the system with key parameters such as suction flow rate and gap thickness. This correlation was established using a simplified model. Experimental setups have confirmed several important findings. Firstly, pressure distribution within the system is observed to be symmetric along the width but non-symmetric along the length. Secondly, it was found that the viscous force increases with the higher suction flow rates or when the gap thickness between the object and the surface is reduced. Moving on to control and performance, a PID controller has been implemented to effectively manage 1D position, control, and tracking of the object. The system demonstrates efficient and precise motion stimulation through the controlled regulation of suction flow rates. The impact of this research is significant. The validated model enables accurate prediction of viscous force, which is crucial for ensuring system stability and operational efficiency. This knowledge can be leveraged to optimize system design, improve performance, and expand the range of applications for contactless air conveyors. Thank you.